Good morning children and welcome back to your chemistry class. We were studying alcohols, phenols and ethers. We had finished with alcohols and phenols and today I shall begin with ethers. What are ethers? They are the organic compounds having the general formula, whose general formula is CnH2n plus 2 oxygen, right? And they are always represented by a general structure of what? ROR dash. Fine. Now let us talk about the structure of ethers. So over here we should know that this oxygen atom in ethers, it shows sp3 hybridization. Clear? And it is attached to the two alkyl groups at an angle of 110 degrees with sigma bond. What is the distance between the oxygen and one of the alkyl groups? It is 141 picometer. Clear? So oxygen atom in ethers, it has what kind of hybridization? sp3 hybridized. And ethers, they always show a bent or an angular structure, and they are dialkyl derivatives of water, or we may say that they are monoalkyl derivatives of alcohols. I hope this is clear to you. Now next we talk about the classification. Okay, classification of ethers. So over here, on the basis of the nature of the two alkyl groups, right? The general structure, as I have already told you, is what? ROR dash, and therefore they are classified into two parts. What are they? One is the symmetrical, or what we can say it is a simple ether, right? And what the other one is your unsymmetrical or mixed ethers. So if it is a simple ether, then you are going to see both the alkyl groups will be same, right? Both the alkyl groups will be same. Then we say that it is a simple ether. But if both the alkyl groups are different, then it will be termed as mixed ether, that is ROR dash, right? Then it will be termed as a mixed ethers. And ethers, they are always written as alkoxy-alkane. What? Alkoxy-alkane. The word this oxy, what you see over here, it is added to the smaller alkyl group in case of mixed ethers. So let's take few examples over here. Like firstly, I'm going to talk about simple ether. For example, say CH3OCH3. So when you see that the two alkyl groups are same, right? Or what we call it as a symmetrical ether or a simple ether, then the prefix used over here will be di. And therefore, what will be the name of it? It will be dimethyl ether. Clear? But what when we have a mixed ether, that means the two alkyl groups are different. In that case, the two alkyl groups that are attached to the oxygen, they are named in the alphabetical order first and foremost, and the word ether is added to it. For example, say CH3O, CH2, CH3. So now what do you see over here? This is your ethyl group and this is your methyl group. And as I told you that the name will be given in the alphabetical order. So ethyl group is going to come first. So what is the name of this compound in that case? Ethyl methyl ether. Right? The word ether will come, then the alphabetical names have to be seen. So this methyl ether, it is a mixed ether. Now let's talk about the IUPAC name. What did I tell you in IUPAC name? we have to use alkoxyalkane, right? So over here for this ethyl methyl ether, what will be the IUPAC name for this? It will be methoxyethane. The IUPAC name of this ethyl methyl ether will be what? Methoxyethane. And that for dimethyl ether, that is CH3OCH3, it will be methoxymethane. So this was the IUPAC name. This was the IUPAC name and this is the common name given to it. So in IUPAC name we are using what? Alkoxyalkane. And in the common name, if it is a simple ether, then the word di will be used over here. If it is a complex or a mixed ether, then what have we to do? The word ether has to come, but the alkyl group has to be written according to the alphabetical order. Clear? Now, what kind of isomerism do we see over here? The isomerism commonly exhibited by these ethers, it is metamerism, right? Like ethanol and diethyl ether, they are the ones which show functional isomers. Let us now begin with the preparation of ethers. So we will do the preparation of ethers today. So for the first one, from alcohols. Okay, so this can be done by two methods. First, using acid catalyzed dehydration, and the second could be only the catalytic dehydration. Okay, so let us do the first one, that is your acid catalyzed dehydration. Okay, over here we are going to use 2 moles of alcohols, or in other word I can say that we are using excess of alcohol over here. So let's take a general formula of it, general reaction to it. ROH plus HOR. What did I say? I am taking 2 moles of alcohol, or I can say in other words that I am using excess of alcohol. Then acid catalyzed. So I have to use an acid over here, that is a concentrated H2SO4 is used over here. Clear? And this reaction takes place at 413 Kelvin. Now remember, this reaction takes place at this particular temperature only, and the temperature should be carefully controlled. Otherwise, at a higher temperature, instead of forming ether, alkene will be obtained as a major product. So over here, although this concentrated sulfuric acid, it acts as a catalyst, but it has to be added repeatedly as the water formed during the reaction, it continuously dilutes concentrated sulfuric acid. So this will affect the dehydration. Thus, we say that when 2 moles of alcohol is used, at what temperature? 413 Kelvin with concentrated sulfuric acid, it is going to form ether. This is the formation of ether plus water is formed. Due to the formation of water, what did I tell you? That repeatedly we have to add concentrated sulfuric acid, as this water dilutes the acid, right? Now remember that the order of dehydration of alcohols which leads to the formation of ether is your primary shows better dehydration than your secondary, followed by your tertiary alcohols. Clear? Now let us talk about catalytic The second one, catalytic dehydration. Catalytic dehydration. Over here we need to use a catalyst, that is when excess of your alcohol is used here also, or what I told you, 2 moles of alcohol I am using over here. Now instead of using concentrated sulfuric acid, here I can use aluminium oxide. At what temperature? 525 Kelvin. And then this is going to form ether and water, right? So let's take an example over here, like CH3, CH2OH. So we take 2 molecules of this alcohol. So plus, then I'll take HOCH2CH3. Okay, in the presence of aluminium oxide at temperature 525 Kelvin, I am going to obtain what? Now see, this and this, they are same. So, and water is formed over here. So, it forms CH3, CH2O, CH2, CH3 plus H2O. Now, since both the alkyl groups are same, so what are we going to name this as? Diethyl ether. Clear? So this was the preparation of ethers from alcohols. One by acid catalyzed dehydration and the other one is only by catalytic dehydration. We move to the next. So before we proceed with the second method of preparation of ethers, let me tell you what the order of dehydration of alcohols I had told you, that primary is shows more dehydration with the catalyst than your secondary or your tertiary. So always remember over here, primary alcohol will always show you SN2 mechanism, right? Whereas the secondary and the tertiary, they are going to show you SN1 mechanism. Okay, this is something that I forgot to tell you in the previous one. Now, coming to the second method of preparing ethers, it could be from haloalkanes, right? So, to begin with, let us start with the Williamson's synthesis, that is by Williamson's synthesis. Now this is one of the best method to prepare ethers, right? So in this method, the alkyl halide, it is treated with either sodium or potassium alkoxide, and this reaction is a simple nucleophilic substitution reaction of halogen atom of the alkyl halide by the alkoxide, right? And this method may be used to prepare simple as well as mixed ethers. So let us look at the general reaction first. So over here, like the alkyl halide Rx, when it is treated with sodium alkoxide, that is RONA. Now this has lone pair, right? And there is a negative and a positive sign here. So what happens? The fission takes place over here, right? The electron moves towards X. So this X, which is now electronegative in nature, will combine with electropositive ion over here. And where will this R go? It will get attached to the one of the lone pairs, and therefore it is going to form the ether, that is ROR. Let me take this as R dash X, so it will form ROX plus NaX. This is the general formula, right? Where this is what? This is called as your sodium alkoxide, and this is your alkyl halide. Is this point clear? Now let me give you one example also, like C2H5Br. What is this? This is your alkyl halide. When reacts with your sodium alkoxide, so what are you going to take over here? Suppose I take C2H5ONA, right? So I'm going to get a simple ether over here because both my alkyl groups are the same. So what did I tell you in the beginning? With the Williamson synthesis, we can prepare both mixed as well as simple ethers. So over here, first I am forming the simple ether. So it forms C2H5O, C2H5 plus NaBr is formed here, right? What kind of a reaction is this? Firstly, this reaction takes place at 330 Kelvin, and this shows you SN2 mechanism, right? Now this method is not applicable when your alkyl halide over here, which is used, is your tertiary, right? So tertiary halides, they are highly susceptible to dehydrohalogenation in the presence of your sodium alkoxides, and they form strong bases. So they do not form the ethers, but they are going to form alkenes, and thus they do not show Williamson synthesis. So Williamson synthesis is only shown by primary alkyl halides. Now the second one is by heating haloalkenes with dry silver oxide, right? So let's take an example over here, like CH3CH2Br. Okay, so we take 2 moles of this alkyl halide, that is plus CH3CH2Br, right? This combines with, as I said, dry silver oxide. So this is Ag2O. Okay, so what does it form? AgBr will be formed, 2 AgBrs will be formed, and your diethyl ether will be formed. So this is going to give us CH3CH2 CH3CH2O. What is this? This is your diethyl ether plus AgBr. Silver bromide will be formed over here. Okay, and then the last part is from haloalkanes is from Grignard's reagent. From Grignard's reagent. So let's do this. CH3O CH2Cl. What is this? This is chloromethoxymethane. Chloromethoxymethane. Okay. When this is treated with Grignard's reagent, that is, if I take CH3MgI, then in the presence of dry ether, it is going to form what? Look here, it will form CH3O, CH2CH3. What is this? This is your mixed ether called as ethyl methyl ether. So ethyl methyl ether plus MgClI. What is the name of this? This is called as chloromagnesium iodide. What is this product called as? Chloromagnesium iodide. I hope all the preparation of ethers is clear to you. So we do only till the preparation of ethers today. Next video I shall come up with the physical and the chemical properties of ethers. Thank you.